Hey there, Mr. Sutton here with the AB Calculus 311 Extra Practice number 3 solutions on derivatives of logarithmic functions. For this problem, I'm trying to find the derivative of this logarithmic function. For this one, I'm going to have to use the chain rule. So for the outer function, I have ln of something. Derivative of that is going to be 1 over the something. So we're going to have 1 over x squared plus 5x. But we're going to be multiplying that by the derivative of x squared plus 5x, and I just might as well put that in the numerator. So that's going to be 2x plus 5. For this problem, I want the derivative of ln of 2x. So this is a small chain rule. We have the ln of something. Derivative of that is 1 over the something, which is 2x in this case. And now we have to multiply that by the derivative of 2x, which is 2. I'll just put that in the numerator here. And no need, but if you really wanted to, you could reduce this to 1 over x. To take the derivative of this function, I'm going to need to use the product rule. So let me set up the box and ribbon here. I have my two factors, 8x to the 7th plus 3, and ln of 8x to the 6th. And their derivatives now, we're going to have 56x to the 6th. And over here, this is a chain rule. So we're going to have, let's see here, 1 over something, 1 over 8x to the 6th, that's the outer function, times the derivative of 8x to the 6th, which is 48x to the 5th. And there's no need, but if you wanted to, you could reduce this to 6 over x. So now multiplying it out with the ribbon, I've got 56x to the 6th times ln of 8x to the 6th, plus, parentheses, 8x to the 7th plus 3 times 6 over x. On this function, I'm trying to find the derivative of log base 2 of x squared. Now, you could treat this as a chain rule and do it that way, or you could use log rules, which I did here. So I saw that I have an exponent in here. Using log rules, I can pop that out as a coefficient and rewrite this as 2 log base 2 of x. And now I'm just doing 2 times the derivative of log base 2 of x, which is 2 times 1 over, and this is going to be x ln of 2, and call it a day. For this problem, I'm trying to find the derivative in terms of x only of this function. So this is one of those where you have an x in both the base and the exponent. So for this one, we're going to have to use the technique of logarithmic differentiation. So we'll start by taking the ln of both sides. So I've got ln of y on the left. On the right, taking the log of this is going to pop out my tangent of x as a coefficient. And then I have the ln of whatever was left, so ln of x. So kind of a chain rule going on here. So now I'm going to use implicit differentiation. On the left side, I've got, let's see here, this is going to be 1 over y times dy over dx. Because I took the derivative of y, I have to multiply by the tail of that, because it's an inner implicit function of x. On the right side, I have a product rule, so let me set up the box and ribbon for that. So I have a tan of x and an ln of x. Derivative of tan is going to be secant squared of x. ln, so this is a chain rule. The outer function, we have ln of something. Derivative of that is going to be 1 over the something, so 1 over ln of x. But now we have to multiply by the derivative of the something, which also is ln of x. So derivative of ln of x that we're multiplying by is 1 over x. Okay, so multiplying it out with the ribbon now, I've got secant squared ln of x, plus, this is going to be, I guess I could just call this tan over x ln of x, if I want to put it all in one nice little fraction here. And at this point, I have to get dy over dx by itself. So to do that, I just have to multiply both sides by y. So that gives me y times all of the stuff that's already over here in a big parentheses. Now, since they said they wanted this in terms of x only, I have to substitute ln of tan of x back in for y down here in the answer. So there is the final answer, just substituted back in. And that's it for that one. For this problem, I just want the derivative of ln of x. So this is a small chain rule. I have the outer function is ln of something. Derivative of that is going to be 1 over the something, 1 over ln of x in this case. Now I have to multiply by the derivative of the inner function, which also happens to be ln of x. Derivative of ln of x is 1 over x, so that's what I'm multiplying by for my tail. And I could just rewrite this as 1 over x ln of x if I wanted, and call it a day. To take take the derivative of this function, I'm going to start by using my log rules. I'm going to pop this exponent of 2 out as a coefficient, so I'll have 2 ln of 9x to the 10th plus 4. And I didn't have to do that, but that's just going to save me the trouble of an extra link when I use the chain rule. But we're going to have to use the chain rule a little bit here. So my outer function, I've got 2 ln of something. The derivative of that's going to be 2 over the something, so 2 over nx to the 10th plus 4. Now I have to multiply by the derivative of n, or 9x to the 10th plus 4. So that's going to be 90 x to the 9th, and that 4 is just a constant, so it's gone. And there's our final answer. For this one, I'm trying to find the derivative of x cubed minus 2x quantity to the ln of x. Now, you might notice here that we have a variable in both the base and the exponent. That means we need to use logarithmic differentiation to figure this one out. So I'll take the log of both sides. I've got ln of y on the left side. On the right side, taking the ln pops this ln of x out, and then I'm multiplying that by the ln of x cubed minus 2x. So going left to right, implicitly differentiating, I've got 1 over y times dy over dx equals, now I have to use the product rule. So I have ln of x and ln of x cubed minus 2x, using this in my box here. Derivatives, we've got 1 over x, and this is a chain rule. We've got the ln of something, derivative of that is 1 over the something, so 1 over x cubed minus 2x, times the derivative of the inner function, which is going to be 3x squared minus 2. And now multiplying it out with the ribbon, I've got, let's see here, I can write this as ln of x cubed minus 2x over x, if I just combine that into one fraction. And then plus, we're going to have this big fraction times an ln of x. At this point, I just have to get dy over dx by itself. So to do that, I'm going to multiply both sides by y, putting everything on the right side in a big old parentheses. And then they did say they wanted dy dx in terms of x only. So this y here, I can't leave this in my answer. I have to replace that with what y actually equals, which in the beginning they said was x cubed minus 2x to the ln of x. So I'll just put that in there instead. And that's it for this one. To take the derivative on this one, I'm going to save myself a little bit of time by popping that 3 out using log rules. So this is really 3 ln of x. And then the derivative of this is just 3 times the derivative of ln, so 3 times 1 over x, or just simply 3 over x. To take the derivative of this problem, I could use the chain rule, but that would be doing it the hard way. I'm going to start by just popping out this 2 using my log rules. So this is really 2 times log base 4 of x. So 2 times the derivative now of log base 4 of x, which is just going to be 2 over x ln of 4. For this no calculator based free response problem, I'm given the graphs of f and f prime, the derivative of f, between -5 and 5. For the first task here, this is part A now, they want the average rate of change of f over the interval -5 to 5. And there's more, but we'll get there when we get there. Let's find the average rate of change. This is going to be f of 5 minus f of -5, all over 5 minus -5, or 5 plus 5. So let me just rewrite that denominator and fill in what those f values are now. F of 5, looking that up in my table, that's all the way up here. That's 9. And f of -5 is back here. That's 3. So we've got 9 minus 3 over 5 plus 5. That's going to be 6 over 10, or 3/5 if we reduce it. Now, we also wanted to know for how many values of x in the interval from -5 to 5 does the instantaneous rate of change equal the average rate of change of f. So we're basically asking, where does f prime of x equal 3/5, or at least how many times does this happen? Now, this would be difficult if we only had the graph of f, but since we have f prime graphed out here, I'm just going to draw a horizontal line through 3/5 up here, like so, and we'll just see how many times that crosses the f prime line. And we can count, right? This is 1, 2 times. We can see that visually. So we're all set on that one, 2x values. For part B of this, we want to write an equation for the line tangent to the graph of f at x equals 2. So for this, I'm going to use point slope, y minus y1 equals m times x minus x1. I don't get anything for writing that, but at least tells me what I'm looking for. So I already have my x1. That's this 2 right here. But I need the y value that goes with that, and also the slope at 2. So for the y value, that's just going to be f of 2, which I can look up in the graph here. So at the x value 2, up here we have a y value of 6. And now for the slope, that's going to be f prime of 2, the instantaneous rate of change at 2. Looking that up in my f prime graph, f prime of 2 looks to be about negative 2. So plugging all this in, we have y minus the y value 6 equals my slope of negative 2 times x minus the x value they gave us of 2. For this part of the problem, they're giving us 2 limits. One is x approaches negative 1 of f of x minus f of negative 1 over x minus negative 1, and this other limit here. They want the value or a reason why it doesn't exist. So they were a little bit sneaky here, but what they're actually asking you for are some derivatives. This is actually, you might recognize the Leibniz form of a derivative. It doesn't get used as often as Newton, but here it is. So they're really saying, hey, what is f prime of negative 1? That's what this first limit is really getting at. Well, f prime of negative 1, we can look that up in the f prime graph. At negative 1, f prime has a value of 4. So that's pretty straightforward. This other one is asking about f prime of 3. What's f prime of 3? Looking that up in my f prime graph, we see that there are open dots there, so that one does not exist. Now, in terms of reasons why it does not exist, if we look back at the f graph, at 3, we have a cusp. So that's why it doesn't exist, because f is not differentiable at x equals 3. And you could say cusp as a reason as well. For this last part of the problem, they're defining g as f of x times ln of x, and they want the value of g prime of 4. So to get this, we're going to have to use a product rule. So I've got u prime v plus uv prime. I don't get anything for writing this, but at least tells me what I'm looking for. So setting up my box and ribbon for this, I've got f of x and ln of x. Those are my 2 factors. And now the derivatives of those, we have f prime and 1 over x. Now before I multiply all this out, I'm just actually going to plug in this 4 inside the box. So if x equals 4, f of 4, looking that up in the graph here, that's going to have a value of 6. And then ln of 4, well, we can't really do much with that. We're just going to leave that as ln of 4. Next, let's look up f prime of 4. So in the f prime graph, f prime of 4, it looks like that is the y value up there of 3. And then finally, this is going to be 1 over 4 down here. Multiplying this out, we've got 3 ln of 4. Now this is g prime of 4 we're getting. 3 ln of 4 plus 6 times 1/4, which you could reduce to 3 halves if you wanted to. So there it is.